Today, I thought that since it's a conference of condensed matter, so let me see if something could be done on my work in relation to the condensed matter. So what we have found that we have done a little bit of work on armor ceramics. Because the ceramics is a material which can defend the bullet or the projectile very efficiently. Because earlier it was metals. Uh,
Sampath,
Earlier it was metals, and now it is transforming to ceramics because of the lightweight. So apart from that, there are many other advantages as well as a little bit of disadvantages also. So still not, it is not very clear how the ceramic failure takes place, and to understand those failure mechanisms, we need to work very carefully, and we have to handle these things in a very efficient way. So let me first tell you those do not know what is ceramics. I think everybody knows what is ceramics, but basically it is an inorganic material which are processed at high temperature. So now the definition of ceramics have changed. So these are basically including a carbon compounds, carbon as well in the ceramics, like carbon nanotube, graphene, etc. So traditionally ceramics were made like terracotta and all these clay, feldspar and quartz made from the clay, feldspar and quartz. So those are all traditional ceramics. You have seen it a lot, and its technology is 3,000 years back. It's a very age-old process. But with the advent of the modern technologies, you got advanced technologies, and for the advanced technologies, you need materials which cannot satisfy the normal conditions. So these materials are called advanced materials, and it is processed also by the advanced technology. That is a very interesting thing. So these advanced ceramics are now coming in different applications. So one of them is armor. Now, these ceramics are aluminum oxide, silicon nitride, silicon carbide, barium titanate, calcium fluoride, silicon. There are a lot of inorganic compounds. You can make it ceramics by processing at the high temperature. Now, let us see how the ceramics fail. If you take a ceramics and drop it, it will break. So its fracture toughness is very low. You cannot compare the fracture toughness of a ceramics with metals or polymers. So its fracture toughness is very low. But even then, when a bullet impacts the ceramics, the bullet fractures. That is the most important thing. The bullet fractures and get crushed. So that is the reason why ceramics are applied in the armor. So a lot of researches are now going on around the world uh, to understand the mechanism of failure and how it is happening. Now here comes the condensed matter physics, which helps us to understand the mechanism of the failure. If you look at it, you can see in the diagram, this is the projectile. When it hits the ceramics at a very high velocity, that means it has got a very high kinetic energy, the tip of the projectile deforms and the ceramics also breaks. Now this breaking of ceramics, if you can delay it, you can restrict the failure. So the tip of the projectile, when it hits the ceramics, it creates a conical shape crack. So these conical cracks are quite common to anything on the impact load and under the shock wave conditions. And shock waves are generated within the ceramics as well as within the projectile. Now, the sign of the shock waves are different in the ceramics and in the projectile. It depends upon how the impedances of the two materials are. Impedances means density and the velocity of sound waves within the materials. So this is the way how the ceramics fails. Now, in the case of ceramics, aluminum nitride, silicon carbide, and are the main. These are the two main ceramics which are advanced ceramics, and which is occupying the states of the ceramic armor materials. Now we have carried out a little bit of work on aluminum nitride. See, aluminum nitride is a woodside crystalline lattice, and hexagonal woodside crystalline lattice, and it has a very interesting properties. If you apply confinement load in a aluminum nitride ceramics, what you will get? You will get transition of the properties from the brittle to the ductile. It's very, I mean, it's very new invention, and people have found that when you apply this confinement load, and then you hit it with a shock wave, you'll get the transition from the brittle to the ductile. So this brittle to ductile transition takes a lot of energy. It consumes a lot of energy of the bullet, and it helps to protect the bullet. So we carried out an experiment with two different ceramics. One is aluminum oxide, the other is aluminum nitride, and wanted to see how this varies with the type of the ceramics, I mean with the chemical composition of the ceramics. So one is AlN, the other one is Al2O3. If you see, and those two have got two different crystal structures. One is having rhombohedral crystal structures, the other one is having hexagonal crystal structures. So our projectile was about 10.57 gram weight, and it hit with a muzzle velocity. Muzzle velocity means when it hits, if you take a gun shot, you can change the muzzle velocity and by changing the composition of the explosives. So by changing the muzzle velocity, maximum it can go up to 847, and we did the experiment with the highest muzzle velocity of the projectile. It is about 847 velocity, and it happens with any AK-47 bullets. So that was our technical interest. Now this is the target which we took. This target is made up of aluminum alloy A, on which we have placed a fiberglass material which is surrounding the ceramics. This ceramics is denoted by C. Then this C portion is hit by the bullet, and later on we have modeled it in the numerical simulations, and we did the work. Now what I wanted to show you is that projectile velocity, when the projectile is hitting the ceramics, gradually velocity goes down. Because it goes down, it breaks the ceramics. At the same time, its own velocity is going down. So this can be simulated. This can be experimentally verified. This can be simulated as well. So we carry out the simulation work. Now if you look at this, you can find that there are two areas. This is the maximum velocity of the bullet. It is going down. And in these two materials where it stops, this time is different. In one material, it is stopping within 42 microseconds. The other one, it is stopping at a much higher time. So much longer time, sorry. So this time difference, what it plays on the property of the ceramics. Here comes the question of ductility within the material. So if you can increase the ductility of the material, you can get a lot of energy absorption as well. So then we looked at the microstructure of the impacted ceramics. What we found that ceramics is, as I told you, ceramics is a very brittle in nature, and that is due to the high Peirce number of stresses. And this brittleness is only because ceramics contains dissimilar ions. While metals consist of similar type of atoms, in case of ceramic crystal structure, you get dissimilar ions. So these ions, when it moves to form a dislocation, what happens? Positive ions comes in close to the another positive ion, and it repels. Similarly, negative ions has got an attraction with the positive ions. So naturally, the bonding between the ions is very strong. So finally, as a result of which what happens, the Peirce-Navarro stress, which creates the shear of the crystal structure, is very, very high. So ceramics are not at all ductile, it is a brittle in material. But when shock waves are coming, this huge shock waves at the shock waves pressure of 50 gigapascal, 50 GPa or 40 GPa. Now this brittleness doesn't play any role. What happens that ions are forced to move from one place to the other, and you get dislocations like this. And this is not only dislocation, you get the domain boundaries also. What we have taken the transmission electron microscope of the failed sample that we have carried out one typical experimental arrangement so that the debris after the impact could be collected, and this debris was analyzed further for future, to understand the mechanism of failure. So from that debris, we have taken the this sample, the thin section. We have seen here the Shockley defect, and Shockley defects are coming, and this Shockley stacking force originated from the dislocations. You can see this is present in the original material. So the original material is also very important. It is present, but in very minor quantities. But when it is shocked, you can see lots of domain boundaries are also there. These are the antiphase domain boundaries, and these are caused due to local shear stresses. So it absorbs lot of energy, and this is a dark field image. You can see clearly the domain boundaries. So this absorbs a lot of energy of the impacted bullet. So this happens in case of aluminum nitride, which is prone to ductility at a considerable confinement pressure. Next, another important ceramics is silicon carbide. The silicon carbide is a very interesting material, as well as aluminum nitride. It can be applied in lot of applications. So one of them is the armor applications. Why it is so? It has got two crystal systems. One is woodside, it is hexagonal, and the other one is cubic, that is sphalerite structure. Now, in case of inorganic materials, what happened? You cannot say hexagonal or you cannot say cubic. You have to identify one analog with it. So here it is sphalerite, it is in the cubic lattice, and the other one is the woodside, it is in the hexagonal lattice. So these two crystal systems of the ceramics. Apart from that, it has got different polytypes also. Polytypes means the stacking of the ceramics are different. I'll show you later. Before that, I want to tell you that there are 200 polytypes of silicon carbide. So most common polytypes are 2H, 6H, 4H, 15R, and 3C. This 3C symbolizes the cubic form. The 2H, 4H, 6H are hexagonal form. I'll show you how it happens and what are the structures. Now, one important thing is that diffusivities of, since these are covalent, so diffusivities of silicon and carbon within their lattice is very low. So you have to apply pressure, high temperature additive to prepare these polycrystalline materials. Now we are dealing with the polycrystalline materials. We are not dealing with the single crystal materials now. So it has got a very high Vickers hardness, about 27 GPa we have got. So it is very high at 1 kg load, and it has got a high sound velocity. That is most important. This high longitudinal velocity as well as transverse velocity within the ceramics. Solids have got much higher sound velocity. That is very important for armor applications. Now, and as well as it has got a low density, about 3.21 grams per cc. Now, regarding the polytypes of silicon carbide, you see these polytypes differ due to, the properties also differ due to the different polytypes. So in these polytypes, what happens? The stacking of 111 silicon carbide bilayers on the, and as well as 0001 of the hexagonal bilayer. It has been found that during processing, you have to add some aluminum or boron or carbon within the material to get it densified to a maximum density, say about 98%, 99% relative density. And you have to add some metal ions like aluminum. What happens? This aluminum goes into the 6H structure, and it converts it to the 4H structure. It creates fault within the lattice, and it then converts it to the 4H structure. So this polytypic transformation is very important in this silicon carbide ceramics. So there are existence of Shockley stacking fault, and there are these are in somebody questions that whether Shockley stacking fault is the only stacking fault, but there are Frank stacking fault as well as present in this material. Now let us see how the polytype structures are there. You can see this is the pure 3C. These are the three stacking layers A, B, C. Then this is the 2H. Then this is the 4H. You've got four ions. There are 6H. You have got 6 ions, and so on and so forth. Now, these are the stacking faults present in the 2H, 4H, and 6H structure. Here it is a case of 6H structures in the zone axis 1, 1 towards 0 and the basal plane. And you get different. Just I wanted to show you that how these stacking faults are in silicon carbide. When we apply shock, as I was telling you, the microplasticity appears. Microplasticity means the ceramics becomes more ductile, and this was first reported by some people like Longi. Then some people have also analyzed the dynamic plasticity of silicon carbide during compressive loading. So these are the previous works I wanted to mention you. So here what happened, that lastly, some people have found that amorphization has been taking place. That means when you are hitting it with bullet, when you are giving it extra shock pressure, shock pressure, the crystalline to amorphous formation, phase formation is there, and from there recrystallization also takes place. These were the mechanisms, and some people have observed it. We will also show you how it happened in our case. So, physical mechanisms behind the inelasticity is still not very clear. Most of the earlier studies have been carried out under the 1D strain or 1D stress conditions, but in case of actual armor, it is the multi-axial strain which plays very important role. So we have carried out our experiments with actual heat of the bullet, recovered the soft specimen, and then carried out the further characterizations. This has not yet been done so far. We have not got any report from anywhere who have done this. So what we have taken the starting powder. If you look at the composition, you can find the 3C composition is only 5.5. Mostly it is 6H powder. So we have started with the 6H powders. Now, when we prepared the ceramics after sintering or hot pressing, what we have found that 6H, the quantity of 6H is reduced while quantity of 4H has increased. This is possible for a polytypic transformation from the structure 6H to the 4H. And later on, some cases where you add a different additive, what you find that your polytype ratios are changed. In this case, you can find in the P2 samples, mostly 6H variety is maintained, and no, very few transformation is there to the 4H and 3C. This is the original ceramics I am talking about. Then I will show you how it happens after the impact with the bullet. Now, inelasticity of ceramics was, first studied by planar shock experiments. Planar shock experiments means you apply a planar wave to the ceramics and then follow the response. And these responses are followed by means of a manganese gauge or a piezoresistive gauges. And you will find the particle velocity, time, and you get a shock Hougonio also. So Hougonio characteristics are very important in case of armored ceramics. Now you look at this thing, about in 1979, it started long time back. So I will mention only one paper, but they have shown that initially very high rise of stress is there, but gradually it deviates from the linearity. It is called, that's the reason why it is inelastic, and it retains its strength at a very high level after it breaks down finally. So this retention, we are very much interested. So we are going to analyze our materials from this retention value. So these are our experiments, and this experiment has been carried out in TBRL for the first time in this country. So this experiment was carried out in TBRL. So our samples, one sample data I am showing it now. You see, the inelasticity comes from this level. When it starts deviating from the linear elastic mode, this point is called elastic limit, named after the scientist who discovered this thing, that is called Hugoniot elastic limit, or HEL. So Hugoniot elastic limit is a parameter by which we can judge ceramics from one to the other, which is very effective. Now, Hugoniot elastic limit in case of this is very high, about 13 GPa. We have found in case of silicon carbide. And further, if you look at the tank, it retains the strength. The stress rises very high, and it retains it for some time. And these are called the plasticity region. So we will then look after the plasticity region. So these are the Hugoniot elastic limit we have obtained for these two ceramics. One is with the aluminum addition, the another is on the aluminum nitride addition with the corresponding solid solution. And this is a different mechanism. I am not going into details into it. But value of the HCl changes with the material. Means the composition of the materials is very important. Crystal structure of the material is another important criteria. Then alignment of one crystal with the other, called the grain orientation, is also very important. So in case of one, we have seen 11.27 GPa. The other one is about 13.42 GPa. Also a little bit on the how are the things. So these are the two microstructures. You can see that here longer grains are obtained. These grains are mainly, we believe, are 6H grains, and this elongation has been taking place in one microstructure. The same silicon carbide, when processed in a different way, the grains are become very smaller. So we carried out our experiments with these two silicon carbides, preferably in line with the commercial armored silicon carbide available in the market, international market. So we developed the material here, and then we carried out our further experiments here. So grain sizes of these are very small. Here the grain sizes is, heterogeneous grain sizes you can find. One is longer, the other one is very small. Now let us see how it happens. Now we have analyzed the XRT samples after the impact. We can find that initially we have started with 51.19% 6H variety. It changes to 78.9% while the 4H is reduced as well as 3C is reduced. That means these phases have transformed with the help of shock wave to 6H variety. So that is a very important observation we could find out. And this observation was also made some people earlier in the year 2000. So this is in case of another variety of silicon nitride. It is not only that, we will find another thing. Then what we did, we carried out transmission electron microscope analysis with these materials. Now, these are the two microstructures, and these are the debris formed after hit with the bullet. You can easily differentiate between these two materials after the bullet hit. One has got very long, very big fragment. The other one is very small fragments. So we took out the fragments near the bullet hit region, and we then carried out sections for the TEM analysis. In this TEM analysis, you can find this is a very long grain I wanted to show you, and these are very small grains attached with it. In the other case, it is very smaller grains. What I wanted to show you that the surrounding small grains are also very important. It has got a lot of defects, and these defects have been analyzed here. This is a bright field TM micrograph of different tilt under different tilt conditions to reveal the microstructures more efficiently. And this is the SAID pattern. This SAID pattern is a double diffraction pattern where from you can analyze that the two different crystals could be identified from this. One is the 6H variety, the other one is the 3C variety, and this is a typical spot patterns of any stacking fault. Now, another important area is where we have found is that amorphous phase, a diffused rings we can found from this TM. This amorphous phase is very important area, and probably we presume that this was present during the sintering process and after, because other materials didn't have this amorphous phase. This is a 3C variety. I'm not going to details of it. What we wanted to say is that lot of dislocation activities were there during the shock process, and while these were in the plasticity region, and these dislocations create defects which you can find later. I am showing you. See, if you look at it, typical Shockley defect, you can find one dislocation creating the defect here, the other dislocation creating another stacking fault here, third dislocation creating the third stacking fault here. This is a typical Shockley defect created by the dislocation and by the shear stresses involved and applied to this material during the shocking. So, conclusion is that microplasticity with defect creation could be observed in the grains of both aluminum nitride and silicon carbide. Then mainly Shockley stacking fault we could identify. We didn't find any frank stacking fault or any other extrinsic faults. Antiphase domain boundaries could also be observed in aluminum nitride. These defects ultimately lead to micro fissures within the ceramic grains. Tiny little crystals could be observed in the recovered samples. So, dynamic recrystallization is the main process of microplasticity, and this has never been reported still now. So, we are going to communicate it very soon. Thank you very much for your attention.